So areas of plane figures is the new topic which we are going to discuss in this session. So as we have seen so many figures in the previous session, a four-sided closed figures, like we have seen the quadrilateral, we have seen the rhombus, we have seen the trapezium, we have seen the rectangle, the square, the kite. So there are different three-sided figures also which have been discussed, like triangle, right angle triangle, isosceles triangle. So these are all the areas or the plane figures for which are called the two-dimensional plane figures, for which we need to find areas. So let's see how an area can be calculated for each of the quadrilateral or rhombus, etc. for the plane figures. So initially I'm going to start with a trapezium. So let's start with area of a trapezium. But before this, we're going to just recap with the discussion on what exactly is a trapezium. So to recap with trapezium, this is to start with area of trapezium. We all know that a trapezium is a four-sided closed figure where one of the pair of sides are parallel. So one pair of sides is parallel, then that kind of a four-sided closed figure or a quadrilateral is called a trapezium. So let's take a trapezium with the basic definition. So in this case, this is a trapezium because I consider these two sides to be one pair which is parallel. The other two sides are not equal nor they are parallel. So this kind of a four-sided closed figure is a trapezium. So let me take a trapezium of this with my suitable dimensions. Say this, I take it as h. This is h. This entirely I take it as a, and this I take it as b. Then if this is height, then this dimension I take it as c, and this particular dimension I take it as t. So with these dimensions, I would like to construct the area of this parallelogram, which is nothing but I'm going to calculate using few of the mathematical properties. This is the height. This is the height. So as you can see this trapezium, if I divide this into three different regions, I find that there is one rectangle out here, there's one right angle triangle on the left, and there's another right angle triangle which is on the right. So at this trapezium is obtained by joining two right angle triangles and one rectangle together in this form. So when I find the area of this right angle triangle and this right angle triangle and area of this rectangle and just add them, then indirectly I get the area of the entire trapezium. So let's try to break it up and then find area of each of the regions, which is 1, 2 and 3. So region 1 is R1, region 2 is R2, and this region is R3. So we will find the area of each of the regions R1, R2 and R3. So when I come to the region R1, I identify that R1 is a right angled triangle. So let me take that triangle separately out here. So this is the right angled triangle which I have taken here, with this being 90, and this dimension is the height of the trapezium, which is h out in this right angled triangle, and this is c. So I'm going to construct the area of this triangle using the basic formula of area of a triangle. So let's start with the region R1, which is a right angled triangle with the following dimensions, where the height is h and one of the adjacent side to the angle, right angle, is given to be c. So as we all know that area of a right angle triangle is half into base into height. Therefore, for this I get area of R1 is nothing but half into base into height. So this is ch by 2. So I get this to be ch by 2 because we have the area of right angle triangle as half into base, which is c, and the height, which is h. So half into base into height is half into c into h, that is ch by 2. So similarly, I take the region R2 and find the respective area. Now in this case, I identify that the region R2 is a rectangle, and let's see what are the dimensions for this rectangle. So this is a rectangle in which my base is B, because when this is B and these two are parallel, so obviously this also is with the same dimension as that of B. So this also is B. My length is B and my width is H, because this acts as the height of the trapezium. So my base is B, or the length of the rectangle is B, and my width of the rectangle is H. Therefore, we know that area of a rectangle is length into width. Therefore, I get B into H. So therefore, area of region R2 is area of rectangle, which is nothing but base into height, length into width, which is BH. So I get this as BH. Now similarly, let's go to the region R3. So for the region R3 is clearly a right angled triangle with the dimensions D and H. So let's draw a right angled triangle independently for the region R3. So I get this region to be a right angled triangle where this is the right angle and my base here is D, and my H is the height of the original trapezium, which also is the height of this right angle triangle. Now, as we know that this is a right angle triangle, its area would obviously be half into base into height, as in case of region R1, as similar as R1. Therefore, to find area of region R3 is nothing but finding area of triangle, right angle triangle, which is nothing but using the formula half into base into height. Your base is D and the height is H. Therefore, the formula substitutes into half into D into H, which is nothing but DH by 2. So I have got three different regions where area of region R1 is CH by 2, and my area of region R2, which is BH, and my area of region R3, which is DH by 2. Now, to find the area of the entire trapezium as given here, it is nothing but finding the areas of the regions R1, R2 and R3 and just summing up. So we have already found area of region R1, which is CH by 2, and area of region R2 was BH, and area of region R3 is DH by 2. So therefore, area of trapezium in this case is area of region R1 plus R2 plus R3. So let's substitute the values of areas of region R1, R2 and R3 as calculated, and then find indirectly the area of the entire trapezium. So therefore, we have area of region R1, which is already calculated as CH over 2. So just I have here CH over 2. Then the area of the region R2, which is calculated as BH, and then the area of the region R3, which is calculated as DH over 2. So this is the area which has been calculated for each of the regions, and then adding up all three areas is nothing but forms area of the entire trapezium, which is required to be found out. So let's take the LCM. Then I get this to be CH plus 2BH plus DH 1 over 2. So the LCM of each of the cases gives me 2 as the LCM, and then the numerators become CH plus 2BH plus DH. So after the LCM, I'll try to take all possible terms which can be taken common out of all the three terms. Therefore, I identify that H is existing in each of the term so that it can be taken common overall, taken out of the bracket. So therefore, I take this H outside the bracket, and then the remaining terms are written inside the bracket, that is C plus 2B plus D. So this is how I obtain the terms inside the bracket once H is taken out. Then what I do is I split this 2B into B plus B, because I need to identify A by splitting B into two different terms. So taking 2B as B plus B, let's see how A is generated from that. Now, by splitting 2B as B plus B, let's see how A is generated from the given dimensions. So taking this 2b as b plus b and this plus d as original, and just splitting this into separated as b plus b. So now with this, I'm going to assemble c plus b plus d together, and then the other b left over besides, because geometrically, as you see the figure, c plus b plus d is nothing but c plus b plus d is nothing but the entire dimension, which is already a. So when you add c plus b plus d, we get a. Therefore this can be written as half into h into a plus b, because this is nothing but a. From the diagram, c plus b plus d is a. Therefore area of trapezium is given to be the formula half h times a plus b. This is the formula for half h a plus b is the formula for area of trapezium. This can also be read as half times height of the trapezium into sum of parallel sides. So area of trapezium can be taken as half into height into sum of parallel sides, which is nothing but half h a plus b unit square for area of trapezium. Now can be seen with this example problem where I had to find the area of this region, the entire region. Now I clearly identify there are 6 sides. So it is a 6-sided closed figure, which is an hexagon. So this is an hexagon, but I had to find its area by breaking this into suitable regions, different regions. So what I do is I understand this problem with breaking this at this junction so that I get a trapezium and a rectangle. Therefore, when I add the area of the trapezium and the area of the rectangle and just add them up, then overall I get the area of this required region. So this is how we try to solve problems which are given in different shapes. Break them into suitable plane figures and then find the respective areas and then add them up so that we get the area of the entire region which is required or which is asked in the question. So coming to this, I break this into the region DEFA and DCBA. So these are the two regions which are broken up for the entire region. So let's find area of this region, which I take it as R1, and this I take it as R2, and then add up region R1 plus R2 so that I get the area of the overall region which is required in the question. So coming to R1, I identify that area of region R1 is nothing but area of trapezium ADEF. As I'm just going to draw the diagram here, I can see that this is the trapezium ADEF. Now how do I find the height of the trapezium? What will be its height? This is the height, and these are the parallel sides A and B. One of the parallel sides is 6 and the other parallel side would be totally 15 centimeters, because when this is 15, even this would also be 15 centimeters. Both are equal. So the parallel sides are 6 and 15 centimeters, which have been identified in case of this trapezium. Now to find the height of the trapezium, I have to find this distance where the whole is 28 and this is 20. Therefore, this height would be nothing but 28 minus 20 gives me this region, which is nothing but the height is 28 minus 20, which is 8 centimeters. Therefore, my height is 8 centimeters. The parallel sides are identified as A is 15 centimeters, B is 6 centimeters, and my height is 28 minus 20, which gives me 8 centimeters. Therefore, this being equal to this is 15 centimeters, which is A. This is 6 centimeters, which is already given as one of the parallel sides, which is 6 centimeters, which is B. And H is nothing but 28 minus 20, which is H, and that is 8 centimeters is the height of the trapezium. So once we know all these dimensions, then my area of region R1 would be area of trapezium ADEF. We already have discussed about area of trapezium, which is given by the formula half H into A plus B. So therefore, I get half H into A plus B when substituted with each of the respective values would give me half times of H times of A plus B, which is 15 plus 6. Now in this case, I get this to be 2 times of 4, which is 8. So 4 times 15 plus 6, which is 21. So on further simplification, gives me 4 ones 4 and 4 twos 8. So this is 84 centimeters square, which is the area of the region R1. So the region R1 is identified with the area as 84 centimeters square. Similarly, I'll try to find the area of the region R2 by identifying the shape and then finding with the respective formula used then and there. So coming to the region R2, the region R2 here is clearly identified as a rectangle with the dimensions 20 and 15 centimeters. So when length is 20 centimeters and width is 15 centimeters, so we can assume the area of rectangle as length into width, so that we get 20 times 15, which is the area of region R2, that is a rectangle. So area of region R2 is area of rectangle ABCD, which is identified in the diagram. Therefore, area of rectangle is nothing but length into width, which is nothing but 20 times 15, because my length is 20 and my width is 15, as can be clearly seen in the diagram above, which is on further simplification through product gives me 15 times 2, that is 300 centimeters square is the area of region R2. Therefore, once I get the area of the region R1 and R2, my next step is area of the required region is nothing but area of region R1 plus area of region R2. So adding up the areas of the region R1 and R2 would give me the area of the entire region which is required. Now in this case, area of region R1 is already calculated to be 84 centimeters square, and for R2 it is 300, so that on addition, so when I add up 84 with 300, I get 384 centimeters square, which is the area of the required region. This is the answer for the given question, which says find the area of this region. We break up the region into different plane figures, which can be found through using of area, and then I get area of the entire region is 384 centimeter square. Writing of units is very important for area or any other problem, because units also equally carry marks. So not writing of units may be penalized for marks in the tests or exams. Now that we have seen the area of a trapezium and how it is constructed through the various different regions, and the proof of finding the area was also discussed in the previous session. Now similarly, we'll try to find the area of a quadrilateral by a similar proof, by dividing the given quadrilateral into two different regions. So let's see what is the formula which we can generate for the area of quadrilateral. A quadrilateral is a four-sided closed figure which doesn't have any specific properties, but the only property out there being that it is a four-sided closed figure. A polygon which is a four-sided closed figure is a quadrilateral. So let's find the area of a quadrilateral by the mathematical process. So initially I take the diagram of a quadrilateral. So the figure for quadrilateral would be randomly a four-sided closed figure in this form. So let me call this as ABCD is the quadrilateral whose area is what I would like to find. So I would like to find the area of the quadrilateral ABCD. So for this, what I'm going to do is I'm going to join one of the diagonal. There are two diagonals for a quadrilateral. So I consider one of the diagonal and just join A to C. So this is the diagonal I consider. From A to C. So let me mark the diagonal AC as D. So if this is the specific diagonal I consider in this quadrilateral, then its respective heights, the perpendiculars dropped from D to the diagonal is taken as D1, is taken as H1, and the perpendicular drop from B to the diagonal is taken as H2. Now, with these two heights where the perpendicular drop from the vertex D to the diagonal is H1 and the perpendicular drop from vertex B to the diagonal is H2 and the diagonal AC is represented with D, I clearly understand here that the diagonal divides the quadrilateral into two triangles, triangle 1 and triangle 2. So there are two regions which I identify in case of breaking up of a quadrilateral along its diagonal. So this is region 1 which I call, and this is region 2 which I call for the next region. Now let me find the area of the region R1, which is nothing but a triangle. We know that area of a triangle is half into base into height. So let's take each of the regions starting with R1. So coming to R1, I find region R1 to be a triangle where the vertices are DAC and my diagonal is D and my height is H1. So when my height is H1 and my base is D, then my area of region R1, this is region R1, so therefore now area of region R1 is nothing but area of triangle ADC, which I identify here, and in turn area of triangle is nothing but half into base into height, the base being D and the height being H1. So this is DH1 over 2 is the area of the region R1. So similarly, I'll try to find the area of the region R2. So what is the region R2? The region R2 is also a triangle which can be identified as an inverted triangle in the shape of this. So this region R2 is identified with an inverted triangle out here down the diagonal. So this is ABC, which is the region R2, and hence I'm going to find area of this region with its dimensions given as D and H2 being the perpendicular. So with these two dimensions, I identify this triangle with the base as D and the height as H2. Therefore, area of region R2 is nothing but area of triangle ABC, which is nothing but half into base into height. The base being D and the height being H2. Therefore, this would be DH2 over 2. So this is the area of the region R2, which is identified in the second triangle considered down the diagonal. And this is the area of the region R1, which is identified above the diagonal in its quadrilateral. Now therefore, if I would like to find the area of the entire quadrilateral, I just sum up R1 and R2. So therefore, area of quadrilateral ABCD is nothing but area of region R1 plus region R2, which is nothing but already calculated with DH1 by 2 plus DH2 by 2, and this on further simplification by taking half D common gives me H1 plus H2. So I get this to be half D into H1 plus H2 because I have taken D by 2 common from both the terms outside the bracket. So this is how I obtain the formula for area of quadrilateral ABCD is nothing but half the diagonal into sum of the two different heights which are taken into consideration. Therefore, in general, if I take the general form, I can write this as area of any quadrilateral is half the diagonal of the quadrilateral and sum of heights along its diagonal from the respective vertices. So this is how I understand the area of quadrilateral in general form, which is nothing but half the diagonal into sum of heights taken along its diagonal from the respective vertices. Heights taken along the diagonal from respective vertices. Now these are the respective vertices which are taken as heights along the diagonal which is considered for finding its height.